Hi, so we will continue with our discussion of transport and just a recap of what we discussed in the previous presentation. We are looking at the mean-medium approximation, which is really the simplest model almost that would allow us to understand and calculate trends of transport as a function of materials parameters. We assume that the material is really composed of discrete sites where the charge would hop between them, which is all that we have discussed so far. And the assumption here is that we take the density of states that describes the entire sample, and we assume that the whole density of states exists at each site. And as we said, this is somewhat similar to assuming that we have a semiconductor with a Gaussian density of states, but the hopping is, or the transport is through hopping over discrete sites. So basically, if we want to calculate the current, we need to evaluate the contribution of hops from this site, for example, to all its neighbors. And because it's a discrete system, it's going to be a sum. But sometimes it is simpler to transform the sum into an integral and to implement some kind of simplifications. But one needs to be careful doing this transformation because there could always be some obstacles on the way. We might discuss that at the end. And the most detailed account of this model can be found in Yochai's thesis that is listed here. We said that we are using this approximation, and in this approximation we assume that Fermi-Dirac statistics hold across the sample with the same Fermi level and the same temperature. And really that means that we assume that charges, when they hop, they would first relax before they make the second hop, which seems very intuitive and correct, because we know that the relaxation on a single molecule is extremely fast compared to the time it takes to hop between sites. But this is really something that only looks correct, because at the end of the day, the sample is not really the sample that we've drawn through the mean-medium approximation. The sample is the real sample where the density of states is spread across the entire film. And if a charge needs to relax, it has to move. You can only go down in energy if you move in space. So really saying that moving in space is much longer than moving in energy doesn't really hold for this system. So then we said we can introduce another method where we divide the density of states into slots to mimic the effect that each slot is actually a different site in the real system. And when we hop, we calculate the hop to a given slot in energy, and it doesn't relax within the same site. It can only relax if it jumps to a lower energy in the next site. We called this approach the energy space master equation, and we'll touch that later, but first we'll look at what we can learn from our simplest approach, which is the MMA. So really there is no such thing like area heating, which we haven't discussed yet what it means, and our model forces equilibrium at room temperature. So this is one of the results. As I said, we can calculate the current through the expression we saw last time. And if we assume that we have a high enough electric field that most of the current is drift, then the mobility is straightforward to evaluate through this expression. And what we see here, the mobility as a function of charge density, and you can see that it goes up. Here it's the Gaussian density of states with sigma 4kT at room temperature. And this rise of the mobility with the charge density is really the reason why we have discussed traps before, because the lower energy sites which are being filled is really the effect that causes the mobility to go up. If we want to look at the electric field dependence, then we see here again we are changing the electric field, and you see there on the log scale there is this straight line where the mobility is increasing exponentially as a function of the internal electric field. The other thing we can see here, and we could see before, that there is an effect of the charge density as well, naturally, and the maximum mobility we can achieve is a given number, and you can reach that maximum either through enhancing the charge density or through enhancing the electric field, and it depends on the sample or the device that you are using. And again, this is just to show that the higher the disorder, the longer the tails, and the enhancement of the mobility as a function of the electric field or charge density is really more pronounced for sigma like 7kT. And if we just concentrate on this linear slope on the log scale, then we can see that it really fits the idea of the mobility being proportional to the exponent of the square root of the electric field, which is what we have seen when we discussed traps. This crossing that jumped here before I was ready for it really is to remind us that what we see here is the classical example where you apply a model and you get a result. And actually, when we did that calculation, we were not aware yet that for sigma larger than 5kT, the mobility is not well defined anymore. And really, for 7kT, the mobility is not, if you like, a good quantum number, as one would say in different circumstances. And this is really, if you like, what is commonly accepted, that the reason that the mobility is increasing in this manner is very much similar to the Pull-Frankel effect. And what we are actually doing in the sample, we are lowering the height of the sites that are farther in the direction of the electric field. So now we have seen how we can easily derive the mobility, and I have only presented one method of calculating the current. There are, of course, many other models. And if you know the current and the electric field is not too low, you can neglect diffusion and you know the mobility. So the next challenge is to find the diffusivity or the diffusion constant. And I remind us that we are, in this course at least, within the device physics model or chemical physics model. We rarely stop and ask ourselves, what does really this letter D mean? Typically, without even thinking, what we have in mind is what is called a Fick's law. And the idea is that if there is some kind of a gradient in the concentration or a fluctuation in the concentration, then as the system strives towards equilibrium, these concentrations would flatten out. And this is what it means, this Fick's law. The other way to think of it is more rooted in the thermodynamics and in the idea that actually at equilibrium, what the system is trying to do is to level the energy. And in that sense, there is another way to write the current, and it appears here. And you can say that it is relative to the derivative in the Fermi energy, or the quasi-Fermi energy. And these two may not look the same, and they are not necessarily the same. But if we are thinking of the low density approximation, or when Boltzmann statistics holds, then you know that it is possible to write the relation between the Fermi level and the charge density in this way. And we can take out the Ni out to form this reference potential. And when this is true and when it holds, then it's easy to show that these two expressions are identical. In this context, it's also interesting to note that in electrochemistry, the Fermi level is often referred to as the chemical potential, or the potential that associated with the charge density. And when they note that we are at the low density approximation, they call it the Nernstein regime. So in fact, you could say, so what do we care how we think of D? As long as they are equivalent or identical, then who cares? But then there is always the issue of high densities. And in some systems, you reach what is referred to as high density quicker than in others. So how do we deal with that, and what does high density implies? So for that, we look again at the graphs we've looked at in the second week's lecture. And this is the calculation of the charge density as a function of the Fermi level relative to the center of the Gaussian, where the Gaussian is the density of states. And what we do is we rotate the axis, and instead of showing the charge density as a function of the Fermi energy, we show the energy as a function of the charge density. And you can see here the straight line, which is the Boltzmann or the Nernstian regime, where this equation holds. And really, you can see that at some stage, there is a deviation, and you can see that actually the energy rises in a much steeper way. And in order to describe this, one of the ways to introduce these effects, which is common in electrochemistry, is to introduce a parameter gamma. And really the role of gamma, it depends on n, and it really helps us to make sure that this equation fits the actual curve of the system. And we've already asked ourselves before, why is this happening, or what does it mean? And we can discuss it when we meet. And it's important to know that also that in electrochemistry, the gamma is called the activity coefficient, and it's the Nernstein regime is identified by the fact that gamma is independent of the charge density. But if it is dependent, then when we take the derivative, we have an extra term, which is due to the fact that gamma depends now on the charge density. So if we look at this derivation, now we can see that there are two terms. The first one is what we've seen before, that is associated with the low density, or you can call it the Fickian diffusion. And then there is an extra term here that is showing that when there is also a gradient in energy, there is an extra driving force, and we can associate it with the diffusion and say that there is something that is making the diffusion larger when we are at higher densities. And this is one of the ways of looking at diffusion enhancement that is associated with the energy rise at high charge densities. Another way of looking at this diffusion enhancement at higher density is to consider what is called the generalized Einstein relation. And we will derive it from the device perspective, and we look at the current continuity equation as it's written here. And what we are thinking of is the regime where these two terms are almost identical, which could be either when the system is at equilibrium and there is no driving force, or it could be when we are at quasi-equilibrium, where the difference between these two terms is very small. We've seen this kind of conditions when we were thinking of contacts and detailed equilibrium before. So when we are in this regime, we can manipulate this equation to derive the relation between the diffusion and the mobility. We see here the electric field, this is the distance, and when we manipulate it a little bit, we get this expression here where we can identify E, the electric field, time dx. And obviously, when we are thinking of devices, then this immediately is being replaced by the voltage drop. The next thing we need to do is to remind ourselves that we are thinking of a quasi-equilibrium. And in that case, we can replace the voltage drop with the change in the Fermi level, or the quasi-Fermi level. And when we do that, we arrive at this final expression, where you can see that the ratio between diffusion and mobility is relative to the derivative of the charge density with the Fermi energy. This is really implies that the density of states, or the shape of the density of states, is going to be important in determining the generalized Einstein relation. And this derivation that I've shown here was taken from the classical book by Ashcroft and Merming, and it is a nice book that's worth reading regardless of these lectures. We can repeat the same type of derivation using the expression that employs gamma, or the activity coefficient, that we've seen 2 slides ago. And if we go through the same type of math and derivation, we can see that there is another way to express the generalized Einstein relation. It is composed of the classical Einstein relation, which is represented by the 1 here. And there is an additional term which has to do with the activity coefficient dependence on the charge density. And really here you can see that when you compare this expression and to what I've said about the generalized Einstein relation in the previous slide, that really the activity coefficient and the shape of the density of states are tightly related. And it's convenient to have this type of expressions too, because some of the systems are not described through a density of states. Many are really described using activity coefficient. And this is why this expression is also useful. So we've seen this straightforward derivation. And if you go over it again, you'll see that the only requirement for this derivation to hold is that the material would obey Fermi-Dirac statistics. And most of the materials we know, which are semiconductors, obey these statistics. So really, Although some people refuse to accept it, this is simply stating that the sample has to be in quasi-equilibrium. The generalized Einstein relation is built into the physics, the basic physics of devices. The question really is why can we manage most of the time without even knowing that it exists? And it has really to do with the charge density or the approximations that we use. And really, if we take this, what looks like a complex expression, and if we assume that the material obeys the Boltzmann approximation, namely it's in a non-degenerate state, then we can really plug this in, and we can see that this funny expression really reduces to 1 over kT, and this is really the classical Einstein relation. So really, as long as it's only the tail of the Fermi distribution that enters the density of states, we are safe and we can use the classical Einstein relation. However, if the charge density is going up and up and up, then the Fermi level goes up, and especially when the Fermi level starts to enter the density of states, we can really ask the question if it would keep on growing exponentially, and we've actually answered that in a lecture that we saw together a few weeks ago. And really this is, if you like, the charge density when we have the Fermi level already entering the density of states, and this is really the question. Is it really going to obey? And of course, if I ask this question, then naturally it's not going to obey, because there is a limit to the range where the Boltzmann approximation holds. And what I meant by we discussed it, if you remember, we were discussing how to define the band edge, and we introduced the charge density in a Gaussian density of states as a function of the position of the Fermi energy relative to the center of the Gaussian. And we saw that there is this range where we see the exponential growth, which is where we have the Boltzmann approximation that holds. We have the range where it's completely full and nothing changes, and we use this to define the band edge. And of course, we know that here is the range where the classical Einstein relation would hold. And the question is what would happen when we leave this regime and we go into the regime where the material become degenerate. And the only thing is to try to have a feeling for is this going to increase or reduce this relation between D and mu. And to save you a lot of guessing, you can see that this is a result of the generalized Einstein relation calculation. And you see here, this is for the sigma equals 4 kT. The charge density that is relevant is really the fraction that we have compared to the total density of states. That's what we call the relative charge density. If we assume that the total density of states is 10 to the 20, then you can translate it here to real charge densities. And you see that if we are going beyond the 10 to the 17 or 10 to the 18, that already a sigma of about 100 MeV would start to make a difference. Of course, if we go to 5, it is more pronounced, and especially if we go to 7, you can see that all across the charge densities you can imagine, the classical Einstein relation doesn't hold. And this looks very impressive, but I remind you that we have to be careful when we discuss a growing of the sigma just like that, because as we said, the expressions or method of calculations would always work. But if we have agreed that for sigma larger than 5 kT, the mobility is not well defined, then there is no meaning to the ratio between the diffusivity and the mobility for such large disorders. So that was it. What regarding the mobility and diffusivity, just really a snapshot at it. There are much more details or models or other ways to look at it. And what I will discuss in the next few slides is just some of the points that may turn out as important and mainly are aimed at showing you that these lectures are really simple way of looking at things. And if you want to become an expert or you want to be actually working with transport, then this course is really, as it is called, simply an introductory and nothing more. We have discussed charge density and electric field dependence of the mobility. Historically, the electric field dependence have been around much longer. And you may wonder what is more important, the one or the other. Of course, such a question cannot be answered because what is more important, it depends a lot important for what, or in which context, which device, etc. So I thought we'll have a quick look at OLED measurements, and we'll simulate a measurement that we deduce the mobility from the data after applying bias to an OLED. And of course, we'll do it in a model. So in the model, what we assume is that if we apply a voltage, then the electric field is constant throughout the device. We know that it's not true, but in the model we can do that. And we also let the charge density increase according to this formula that we have derived in the context of space charge limited diodes. So we run such a simulation and calculation, and you see we have a linear line on a log scale, meaning that the mobility is increasing exponentially as a function of the square root of the voltage or the square root of the electric field. And that immediately links to our discussion of traps and barrier lowering. And indeed, it is commonly accepted that for disordered materials, when you apply electric field, the mobility goes up exponentially like the Poole-Frankel effect, simply because the sites, the direction of the field are being lowered, so it becomes easier to hop. But as I said, we have both electric field and charge density in these simulations. And you'd be surprised to know that what I used here is a model by Corhun, who was using percolation only. Mainly what you see here is only the charge density dependence. So there is no electric field contribution at all in this model. The next thing that we can do is we can use our mean-medium approximation, where we have introduced specifically also the barrier lowering, not just the charge density. Of course, this is not the perfect model, but it is rather useful, as you'll see. And we add it here, and you see the effect of barrier lowering is minimal. You know, is almost negligible compared to the charge density dependence that we find in an OLED, simply because the charge is going up. The next and third level, remember we have also a model that doesn't force the charges to remain at the room temperature. It also allows for carrier heating. And if we run that, you see, now we have an effect of electric field. So I know it is very disappointing because most of us definitely know that the electric field dependence is really a result of barrier lowering, but I'm sorry to let you know that it is actually carrier heating effects. The idea that it is mainly barrier lowering was introduced through Monte Carlo simulations, and it wasn't really tested there if there was any carrier heating. It was just intuitively sounded correct, and we all accepted it. But luckily, we made these simple models, and we were able to separate between the carrier heating and the barrier lowering, which is not an easy thing to do. If you would like to go a bit deeper into transport, then there are a bit more details in a review paper that I wrote a long time ago. There are quite a few models by different authors. We have added since another contribution which I like. Maybe you will like it too. But in general, if you are looking for papers and you would like really to study, you need to find papers by people who are writing the papers carefully, and these are two which I would recommend. These are not the only two. So, but I chose them because they are pretty senior, so all the others won't feel embarrassed or annoyed that I didn't mention these names. But if you look at the paper by these two, you are definitely safe. Lastly, I wanted to go back to the generalized Einstein relation and to ask you, really, we went through this procedure and defined the diffusion constant. And actually, what does it mean when we define it this way? Usually, when we look at diffusion, we think of the random walk. We think of a charge being bounced and scattered, etc. And this doesn't appear here at all in this derivation. It's very different. So actually, what we are demanding here or requiring is that Fermi-Dirac statistics will be maintained. So if your, as I said, if your material is going to obey thermodynamics, then the generalized Einstein relation is applicable. And the only reason it's there is to make sure that the charge density would follow the Fermi-Dirac statistics. Of course, if the density is low, then all you need is the Boltzmann approximation, and that is good enough. But this is a different perspective relative to the random walk, which is often more popular in physics papers. Lastly, just a word of caution if you are running simulations. So the good thing is that although the generalized Einstein relation doesn't really appear in many simulation programs, they do include a flag that allows you to use Fermi-Dirac statistics, and this is really the same. If Fermi-Dirac statistics are obeyed, then one way or the other, the generalized Einstein relation is also being implemented. The thing to look out for is that commercial solvers, as it says here, they need to be efficient. So there's also some kind of approximation. Some of them develop the approximations for silicon, where the effective density of states is very high, definitely much higher than gallium arsenide or perovskites, and their approximations are not always good enough. So you have to check and be sure that you know what you are using. Good luck and see you next time.